Hello friends, so today we are going to solve 4 questions, and these 4 questions are with respect to our electric field around the conductors. One second. Okay, so first question, and it states that consider a parallel plate capacitor with different magnitude of charge on the two plates. Let the charge be Q1 and Q2, which we normally set equal to Q and minus Q. Find the 4 amounts of charge in the inner and the outer surface of the plates. So it has to be find the amount of the charge, not 4. So we are given that a parallel plate capacitor is given to us. So let us draw. This is plate number 1 and this is plate number 2. Plate number 1 is suppose having a charge of Q1. Plate number 2 is having a charge of Q2. And we are going to solve this in a more traditional way and try to find out where the formula comes from, the Q1 and Q2 that we normally use. And for that we are going to assume that the charge distribution, because there are 4 surfaces, one surface is towards the left of our Q1, other surface is to the right of Q1, and then same to our Q2 and our Q4. Okay, so we assumed there are 4 charge densities, 2 associated with plate number 1 and 2 associated with plate number 2. And both the plates are having area A. Okay, that's not much of discussion there. Okay. Therefore, you can say that the outer surface of plate 1 outer surface of plate 1, let us suppose that is sigma 1, and then we come to inner surface of plate 1, inner surface of plate 1, that is sigma 2, and then we are having inner surface of plate 2, inner surface of plate 2, that is sigma 3, and finally we are having outer surface of plate 2, that is sigma 4. And with respect to our this charge conservation, so we can write that for charge conservation, the basic formula we can write is our for plate 1 will be equal to total charge and divided by the area. This was for with respect to plate 1, and similarly we can write for plate 2 that their surface charge density will be equal to the total charge and divided by the area. And so we are going to find out how this formula basic is going to be derived. And for that, we know that our electric field inside the conductors is equal to 0. We know that our field inside the conductors is equal to 0. And therefore, we are going to consider a Gaussian pillbox that is inside plate 1. Okay. And from there, we are going to find that the field inside the conductor must be equal to 0. Okay. And that field will be the contribution of all the 4 charges. Okay. Therefore, we are going to consider a Gaussian pillbox inside plate 1. Inside plate 1. And like I said, that our field inside the conductor should be equal to 0. And we also know that the contribution will be from all 4 surface charges. Okay. So you can say the field contribution will be from all 4 surface charges. All 4 surface charges. And for the sake of simplicity, we are going to take that toward the right, we are going to take it as a positive. Therefore, we can say that the field inside plate 1, electric field inside plate 1 will be equal to, and that will be because of our 4 surface charges. First one will be sigma 1, and that is about 2 epsilon naught minus sigma 2 upon 2 epsilon naught minus sigma 3 upon 2 epsilon naught and minus sigma 4 upon 2 epsilon naught. Okay, and this field inside the conductor should be equal to 0. And so 2 epsilon naught, we can just ignore that part, and we can write from here that sigma 1 minus sigma 2 minus sigma 3 minus sigma 4 is equal to 0. Similarly, we can write for plate 2. Okay, we are going to consider a Gaussian pillbox inside the plate 2. Okay. And here we have to remember that this plate 1 is something like this. Okay. These are the plates. Okay. So this is plate 1, and similarly there will be plate 2 also. Okay. Then only it's possible to draw the Gaussian pillbox inside the plate 1 for the first case, and then for plate 2. Therefore, we can write similarly for plate 2, we can write the electric field inside our plate 2 will be equal to sigma 1 upon 2 epsilon naught plus sigma 2 upon 2 epsilon naught plus sigma 3 upon 2 epsilon naught minus sigma 4 upon 2 epsilon naught, and this is equal to 0. And from here we can simply ignore this 2 epsilon naught, and it gives us sigma 1 plus sigma 2 plus sigma 3 minus sigma 4 is equal to 0. And so we are having two equations. Let us put this equation number 1 and this is our equation number 2. And if we add equation 1 and 2, equation 1 plus equation 2, this gives us that twice sigma 1 minus twice sigma 4 is equal to 0, which gives us that sigma 1 is equal to sigma 4. And if we subtract 1 from 2, 2 minus 1, and this is going to give us twice sigma 2 plus twice sigma 3 is equal to 0, so which gives us sigma 2 is equal to minus of sigma 3. So we got the respective charge densities. Okay. So it means that the outer surface have the equal charge and the inner one are having equal but opposite charge. Okay. If you look closely, the outer are having the equal charge and this inner are having the equal but opposite charge. Okay. That we came to the conclusion from their charge densities. And let us find out the respective values. And we have already written that for plate number 1 and this is for plate number 2. Okay, so let me rewrite them again. So we have our sigma 1 plus sigma 2 is equal to our Q1 upon A. Okay. And for our plate 2, we are given that sigma 3 plus sigma 4 is equal to Q2 upon A. Okay. And in place of our sigma 3, we can write this our minus of sigma 2, and in place of sigma 1, we can write sigma, in place of sigma 4, we can write this sigma 1. So this we get sigma 1 minus sigma 2 is equal to Q2 upon A. Okay. So we get the two equations. Okay. Let us put this equation number 3 and this is equation number 4. Now we can solve these equation 3 and 4. So you can say from 3 and 4. Now if we add them, we are going to get this as our, this will be sigma 2. Okay, so this will be twice sigma 1 is equal to our divided by A Q1 plus Q2. So we get this sigma 1 is equal to our Q1 plus Q2 upon A. And if we subtract them, we get this as our twice sigma 2 is equal to Q1 minus Q2 upon A, which gives us sigma 2 is equal to Q1 minus Q2 upon A. And we already know that our sigma 1 is equal to sigma 4. So their value will be same, that is Q1 plus Q2 upon A. And our sigma 3 is minus of sigma 2. Okay. So from here we get our Q2 minus Q1 upon A. So we got the respective charge densities. Okay. And okay, so this was required to find the amount of charge on the inner and the outer surfaces. Okay. And then we come to our special case, which states that if you put Q1 and minus Q in place of Q1 and Q2. So our Q1 is equal to our Q, and Q2 is equal to minus of Q. And so we get that our Q1 is this charge density, that is sigma 1 sigma 4 will be equal to our Q minus Q upon A, which gives us 0. And this sigma 3, which is minus of sigma 2, this comes to us as our, okay, because of negative sign, let me rephrase it. Here we had our sigma 2 is equal to Q1 minus Q2. So we can say sigma 2 is equal to Q1 minus Q2. So this comes as our Q1 and minus Q2 upon A. And this comes as our 2Q upon A. And our sigma 3 will be equal to minus 2Q upon A. And also we want to find out the total charge. So total charge will be equal to the respective charge densities, Q1 plus Q2 upon 2. 1 second, sorry. Yes, I forgot to add 2 here. That was mistake on my part. 1 second. So we get this as our this will be our two, and this will be also 2. Okay. And here also 2, and this is also 2. And here also, okay, this will be our divided by 2, and this is divided by 2. 2 and 2 goes away, and this comes is equal to our Q. 2 and 2, this is our minus of Q. And so we can say the total charge will be Q1 plus Q2 and plus Q1 minus Q2 upon 2 plus Q2 minus Q1 upon 2, and finally our final part is our Q1 plus Q2 upon 2. And so we can clearly see that if we take our LCM, so this plus, this minus, this minus, this plus, it goes away. Okay. And we are left with twice Q1. So you can say this is Q1 plus Q2 upon 2. 2 and 2 goes away. This comes as our Q1 plus Q2. So this is our total charge is equal to the summation of our this one second. Okay. So we can easily say that both the plates are going to have the same charge, and that's all that was required for us. And yeah, I think that is sufficient because it is this much only required. Next question. states that consider a capacitor made of 4 parallel plates with large area A, evenly spaced with a small separation S. First and third are connected by a wire as they are second and fourth. What is the capacitance of this system? So this type of question has been dealt many times, and here it is only given with respect to the statement. So we are given 4 plates. So let us suppose this is plate number 1, plate number 2, plate number 3, and we are having plate number 4. And we are given that the first and third are connected, and second and fourth are connected. That is given to us. And each is having area A, and S is the separation between the plates. Okay. So from here we can easily see there are 3 gaps between the plate. Okay, so this is gap number 1, gap number 2, and gap number 3. And let us assume that this is our potential at plate number 1, potential at plate number 2, potential at plate number 3, and potential at plate number 4. Later on we can adjust according to their connection. And there are 3 gaps, so we can say that each gap is going to behave like a parallel plate capacitor. So we can say that there are 3 gaps each behaving like parallel plate capacitor. Parallel plate capacitor. And for parallel plate capacitor, if their capacitance is C0, then the C0 will be equal to epsilon A upon the space between them, that is our S. Now we come to that with respect to their potential. Okay. For the sake of convenience, let us assume, because plate number 1 and 3 are connected, so let us assume that plate number 1 and 3 are having a 0 potential, and plate number 2 and 4 are connected, and let us suppose they are having a potential V. So we can say let our potential at 1 will be equal to potential at 3, and suppose that is equal to 0, and potential at 2 will be equal to potential at 4, and let us suppose that is our V. So it means that the potential difference between 2 connected conductors is equal to V. From here we can say that potential difference between the 2 connected conductors is equal to V. And let us analyze each gap. Like I said, there are total 3 gaps. Gap number 1, gap number 2, and gap number 3. So let us make an analysis of each gap. And first is gap 1 and 2 between plate number 1 and plate number 2, and in that case the potential difference between plate number 1 and plate number 2 is equal to V. And if the charge between these two is suppose Q12, so this will be equal to C0 times V. Okay. And so plate 2 is at a higher potential, okay, and plate 1 is at the lower potential. Therefore, from here we can say the plate 2, which is at a higher potential, it gets plus C0 times V, and our plate 1, it gets minus C0 times V. Similarly, we come to our gap 2 and 3. Gap between plate number 2 and plate number 3. Once again, the potential difference between the two is our V, and our charge is, let us suppose, Q23, which will be equal to our C0 times V. Similarly, we can write that our plate 2 is going to get plus C0 times V, and plate 3 is going to get minus C0 times V. Now we come to our third gap, that is gap between 3 and 4. So we are having a potential difference of our V, and charge is suppose Q34, which will be equal to C0 times V. And we can write that plate 4 will be our plus C0 times V, and plate 3 will be equal to minus C0 times V. Now we are going to find out what will be the total charge of each connected conductors. Total charge of each connected conductors. And we are first and third, second and fourth are connected. So we start with our first and third. So we have a conductor first and third, and we know that our plate 1 is our C0 negative of C0 V, and plate 3. Now this plate 3, it is going to receive charge from two gaps. Let me draw it here. So this is our 1, 2, 3 and 4. Okay, so plate number 1, plate number 2, plate number 3 and plate number 4. And we are having 1 and 3 are connected, and 2 and 4 are connected. So the plate number 1 is having a charge of minus C0 times V, and this plate number 3 is going to receive a charge from two gaps. Okay. There will be gap number 2 as well as gap number 3. So we can say plate 3 receives charge from two gaps. Okay. it will be coming from gap number 2 and 3, and this will be giving us minus C naught times V, and there will be gap between 3 and 4. It will be also giving us minus C naught times V. So it means the charge of our total charge between our 1 and 3 will be equal to, this is minus C naught V and minus C naught V. Okay. So this will be minus C naught V, minus C naught V, and minus C naught V, giving us minus thrice C naught V. Okay. Similarly, we can write for our conductor 2 and 4. Conductor 2 and 4. And plate 2 is going to receive, this is plate 2, it is going to receive a charge from gap number 1 and gap number 3. Okay. Therefore, we can write that plate 2, it is going to receive from gap number 1 and 2, and the charge value will be plus C naught times V. And it is also going to get the charge from 2 and 3, and that will be plus C naught times V. And we are having plate number 4, and plate number 4 is from gap 3, 4, that is equal to plus C naught times V. Therefore, we can say total charge between plate number 2 and 4 will be equal to the summation of all three, that is C naught V plus C naught V plus C naught V, giving us thrice C naught V. And let's find out now the capacitance. Okay. Now if you look closely, you can clearly see that the magnitude of the charge is same, only the sign is opposite. Okay. And so we can say the capacitance and so we are only interested in the magnitude, so we can say the magnitude of charge stored, let us suppose that is our Q, is equal to 3 C naught V, and we already know that our C is equal to Q upon V. Therefore, we can say that our C is equal to thrice C naught, and we already know value of C naught, so we get C is equal to thrice epsilon naught A upon S. So this is the resultant value of our capacitance that was supposed to find out. We can use the energy method also. We take, because we have 3 gaps, so we are going to have 3 energy, and the total energy will be then 3 by 2 C naught V square, and from there we can just take the equivalent part, and it is going to give us the same answer. Next question. It states that a capacitor consists of 3 concentric cylindrical shells with radii r, 2r and 3r. The inner and the outer shells are connected by the wire, so they are at the same potential. The shells start neutral, and then a battery transfer charge from the middle shell to the inner and outer shell, or outer shell. Inner and outer are connected, so both will be getting the charge. So based on this, we are having these 3 parts. First part states that if the final charge per unit length on the middle shell is minus of lambda, what is the charge per unit length on the inner and the outer shells. Part B, what is the capacitance per unit length of the system. And part C, if the battery is disconnected, what happens to the 3 charges per length on the shell if lambda nu is added to the outer shell. So this is the basic question. And we are given that we are having 3 shells of different radii. So let us suppose this is our radius 1 and this is 2r and this is our 3r. So we are having r, 2r and 3r. And so this is our 1, 2, 3, and we are given that the first and the last one, inner and outer, are connected. So they are connected with each other. So basic connection means they will be at same potential. Okay. Therefore we can say that shells 1 and 3 are connected. Which means same potential. Or we can also call them equipotential. And it says that when the battery transfers the charge from the middle to the inner and outer, okay, and the final one is having a charge density of minus of lambda. Okay. So first of all, let's try to identify the capacitors, because this is going to form a capacitive circuit. Okay. And for that, we are given that 1 and 3, they are connected with each other. Okay. So it means we are going to have 2 capacitors. Let us call this capacitor A, and this capacitor A, it will be formed between shell number 1 and shell number 2. Shell 1 and shell 2, and then we come to our capacitor B, and this capacitor B will be formed between shell number 2 and shell number 3. So we are going to have 2 capacitors, okay? Capacitor A and capacitor B. And we already know that our cylindrical capacitor, if it is having a inner radius Ri and outer radius R naught, so its capacitance we already know, that is a standard formula. So we can say for a cylindrical capacitor, inner radii is suppose Ri and outer radius is suppose R naught. Therefore we can write that its capacitance is suppose C prime, then this C prime will be equal to 2 pi epsilon naught natural log of our R naught upon Ri. This is a standard formula for our cylindrical capacitors. And so we are having 2 cylindrical capacitors. So therefore we can divide this formula into 2 parts. One is our Ca prime, and that will be equal to our 2 pi epsilon naught natural log of our outer, that is 2r, and inner is r. So this comes as our 2 pi epsilon naught natural log of 2. Similarly, CB prime will be equal to our 2 pi epsilon naught natural log of our 3r upon 2r, which gives us 2 pi epsilon naught natural log of 3 by 2. Now we are going to use our equipotential. Okay. So shell number 1 and 3, let us suppose, is having potential V1 because they are connected, so they are going to have the same potential. So we can say that potential at 1 and 3, let us suppose that is our V1, and potential at 2 is, let us suppose, our V2. So we can say the potential difference across capacitor A, therefore we can write that our potential difference across capacitor A will be over V2 minus V1, and potential difference across capacitor B will be equal to our V2 minus V1. Okay. So it means both capacitors have the same voltage across them. Both capacitors have same voltage across them. And that is our delta V is equal to V2 minus V1. Now let's find out what will be the charge on each capacitor. So we can say we are having capacitor A, and this capacitor A is our shell 1 is our inner and shell 2 is our outer. So 1 is our on the inner side and 2 is on our outer side. Therefore, we can write charge on shell 1 charge on shell 1, let us suppose that is a QA, and this QA will be equal to the capacitance and the potential difference. And charge on our shell 2 inner surface, you can say charge on shell 2 and inner surface. And that will be equal to minus of our QA, because this is our shell number 1 and this is our shell number 2. So we are having QA on shell number 1, so the inner surface is going to have our minus of QA. Now we come to our capacitor B, and capacitor B, we are having shell number 2 as the inner and shell number 3 as our outer. Therefore, we can write our charge on shell 3 charge on shell 3, that is our QB, will be equal to CB prime times delta V. Okay. And charge on shell 2 outer, charge on shell 2 and its outer part, outer surface, will be equal to minus of our QB, because suppose this is our shell number 2 and this is our shell number 3. So shell number 3 is having a charge of our QB, so the outer part is going to have a charge of our minus QB. And we also know that the inner surface is going to have a charge of minus of QA. Therefore, we can say total charge on shell 2. Total charge on shell 2, and let us call this our Q2, is equal to minus of QA and minus of QB. And with respect to the substitute with respect to the capacitance, so this case negatives, we have this CA prime plus CB prime times delta V, and we are given that it is having a charge density of lambda. So this will be equal to our minus of lambda. Okay. Therefore, we can write that our CA prime plus CB prime, this was a negative, times our delta of V is equal to minus of lambda. So this minus and minus cancels out, and from here we get that our delta of V is equal to our lambda upon CA prime plus CB prime, okay, and which will be nothing but greater than 0. Therefore, our delta V is greater than 0, which is it is positive. Therefore, we can say that our V2 is greater than our V1. This conclusion we can draw from here. Now, let's calculate the charges on shell number 1 and shell number 2. Charges on shell number 1 and shell number 3. So we can say for shell number 1, that is our lambda 1 is equal to our QA, and that will be our CA prime times delta V. We already know our CA prime as well as, so we can write this as our, we already know delta V, okay. This is our delta V, so we substitute it, we get this as our CA prime divided by CA prime plus CB prime times delta. Okay. And we already know that our CA prime as well as CB prime. So we get this as 1 upon natural log of 2, 1 upon natural log of 2 plus 1 upon natural log of 3 by 2 times lambda. And we can just easily sort it out. So we get lambda 1 will be equal to our natural log of 3 by 2 divided by natural log of 3 times lambda. So this is the charge density on our sheet number shell number 1. Similarly, we can write for our shell number 3, lambda 3 will be equal to our QB, and this we get our CB prime times delta V. So this is CB prime divided by CA prime plus CB prime times lambda. Okay. And So similarly, I'm just going to write the result directly. Natural log of 2 and natural log of 3 times lambda. So we got the respective charge densities on our this shell number 1 and shell number 3. Now we come to part B. In this case, we have to suppose to find out the capacitance per unit length. We have part B, and we have to find out the capacitance per unit length. Capacitance per unit length. And we can, because 1 and 3 are connected, so we can say that the total charge on conductor 1 and 3 will be equal to respect to their charge densities. So you can say that total charge on 1 and 3, let us call this as Q total, and that will be equal to lambda 1 plus lambda 2, which is equal to over lambda. And the voltage, we already know that is our delta V is equal to over lambda upon Ca prime plus Cb prime. Therefore, we can say that our C prime will be equal to our Q total upon delta V, and which we can write as our Ca prime plus Cb prime, and we substitute the values. So we get our C prime will be equal to is 2 pi epsilon naught natural log of 2 plus 2 pi epsilon naught natural log of 3 by 2. And we can just solve it a little bit. So we can just take 2 pi epsilon naught as common. So this comes as 2 pi epsilon naught. This will be natural log of over 3 divided by natural log of 2 multiplied by natural log of 3 by 2. So this is our C prime. That is capacitance per unit length that was asked for. Now part C is very important here, because previously the battery was connected and we solved everything with respect to the battery is already connected. But in part C it says that we have disconnected the battery, and then we added you can say a new charge density, that is lambda nu. Then we have to find out everything. Okay. So we are having this part C, and it part C states that battery is disconnected and lambda nu is added to outer shell. But okay, so now in this case we already know that once the battery is connected, the total charge is going to remain same. Okay, because now the conductor, which is basically here the capacitor, are now isolated. Okay, so the total charge is going to be conserved. Okay, this is a important part here. So we can say that when battery is disconnected, total charge is conserved. let's come to our, because the conductor 1 and 3 were connected to each other, so we can say our conductor 1 comma 3, they were initially neutral, but now we have added a charge. Okay. So we can say conductor 1 and 3 was initially neutral. Okay. And then had a charge lambda distributed as lambda 1 plus lambda 3, distributed as lambda 1 plus lambda 3, which was obviously equal to lambda. And now we are given that lambda nu is added to the outer shell, and this outer shell is shell number 3, and shell number 3 is connected to shell number 1. Okay. So initially this shell number 3 was having a charge density of lambda, and when we are giving a new charge density, basically charge, that is lambda nu, to shell number 3. Okay. And this will be automatically into our shell number 1 also. Okay. So we can say after adding lambda nu to shell 3, total charge on 1 and 3, that will be equal to their initial and the added one. Okay. And this, now the battery has been disconnected, so the conductor 2 is isolated, so its charge will be same that was our previous one. So we can say that our conductor 2 remains isolated. With fixed charge and that is equal to our minus of lambda. And also 1 and 3 are connected, so obviously they has to be at the same potential. Okay. So we can say that our so 1 and 3 are connected, so they are going to have the same potential. Okay, this we have to remember. Now we can find out what will be the respective potential difference. You can say that the potential difference, because we are having 3 individual conductors, conductor 1, conductor 2 and conductor 3. Okay, or basically we are having 2 capacitors. Okay, capacitor 1 and 2 and capacitor 2 and 3, that will be called as A and B. And so we can say that our potential difference, so it means our phi 1 minus phi 2 will be equal to our lambda 1 prime and 2 pi epsilon naught natural log of 2. Similarly, for our capacitor B, this potential difference will be equal to lambda 1 prime plus lambda 2 prime 2 pi epsilon naught and natural log of 3 by 2. And we know that the potential of first and third, they should be at the same potential. So from here we can say potential of 1 should be equal to potential of 3 because they are already connected with each other. Okay. Therefore we can say that for phi 1 is equal to phi 2. So we can say this is phi 1 minus phi 2 plus phi 2 minus phi 3. Okay. So in place of our phi 3, we can easily write our phi 1. Okay. So therefore, all the terms, their summation will be equal to 0. Now we substitute their respective differences. So we get this as lambda 1 prime natural log of 2 divided by 2 pi epsilon naught plus lambda 1 prime lambda 2 prime, and this is about 2 pi epsilon naught natural log of 3 by 2 is equal to 0. And we know that our lambda 2 prime is for our conductor 2 and its value is minus of lambda, that is given to us. Therefore we can write this as our, we can just ignore the denominator and we get this as our lambda 1 prime natural log of 2 plus lambda 1 prime minus of lambda and natural log of 3 by 2 is equal to 0. Okay. And we can solve this and find out the relationship between our lambda 1 prime and lambda, which will be coming as lambda 1 prime is equal to our natural log of 3 by 2 natural log of 3 times lambda. Okay. And this is nothing but same, that is the charge on shell 1. So you can say, because charge on shell 1 we already calculated and this was our charge on shell 1. Okay. So it is same. So it means when we added a new charge on shell number 3 which was connected with shell number 1, the new charge on shell number 1 is same. It is not going to change. So we can say the charge on shell number 1 does not change. Does not change. And now we can find out for our shell number 3. We can say that our lambda 3 prime is equal to our lambda plus lambda nu, okay, minus lambda 1 prime. Okay. So we substitute it, we get this as lambda plus lambda nu minus lambda, and this is natural log of 3 by 2 and natural log of 2. Therefore we get that our lambda 3 prime will be equal to our lambda nu, and we can just combine these two terms. Okay. And this will be our plus lambda, we can take as common, so it will be coming as 1 minus, and you can take natural log of 2 as LCM, so this will be minus minus. Okay, so this will be coming as natural log of 2 divided by natural log of 3. So this is our new charge on our shell number 3. So it means the charge on shell number 1 is going to remain same, it is not going to change. Charge on shell number 2 is also not going to change. Only thing that is going to change is charge on shell number 3. Okay. Because shell number 2 was isolated, okay, so there is nothing new added to it, and this shell number 1 we just calculated is going to have the same charge, and this shell number 3 is going to have also a new charge. Next question. It states that a parallel plate capacitor consists of fixed plate and a movable plate that is allowed to slide in the direction parallel to the plates. Let x be the distance of the overlap as shown in the figure. The separation between the plates is fixed. Figure is given to us, two plates, the lower one is fixed, upper one is movable, and the overlap is said to be given as our x, and the distance is fixed between the separation. Part A. Assume that the plates are electrically isolated so that their charge plus minus Q are constant. In terms of Q and the variable capacitance C, derive an expression for the leftward force on the movable plate. Part B. Now assume that the plates are connected to a battery, so the potential difference phi is held constant. In terms of phi and capacitance C, derive the expression for the force. And part C, if the movable plate is held in place by opposing force, then either of the two setups could be relevant one, because nothing is moving. So the forces in A and B should be equal. Verify that this is the case. So we are supposed to deal with the force, and for that we are going to use the concept of energy, and from energy we can easily find out the force. And we have to remember that only one plate is moving, other plate is fixed, and the movement is along, you can say, the horizontal plane. The vertical distance between the two is fixed. So this distance is fixed, only the, you can say, the length, overlap length is going to change. So let us assume that the separation between the plates is D, okay, and the plate width is suppose our W. Okay. And if you want to use this unit width, we can also use our unit width. That's not a big problem, okay, because nothing is going to change much with respect to width. Okay. So we can say that they are having fixed separation and let us suppose that fixed separation is over D. Okay. Therefore we can say that the plate width is suppose over W. So from here we can find out the area of overlap. Area of overlap, that is of A, will be equal to over X times W. Okay. And from here we can find out the equation of our capacitance. So we can say capacitance C of X will be equal to standard formula epsilon naught A upon D. And we can substitute our A, this is epsilon naught X omega upon D. And only the variable associated here is our X. Therefore, for the sake of simplicity, let's write this as alpha times X, where this alpha is equal to over epsilon naught omega upon D. Okay. Therefore, from here at least we can say that our this capacitance is proportional to X. Okay, one conclusion we can draw it from here. Next, we are supposed to find out the part A. It is given that they are electrically isolated, okay, and it is having a charge Q. Okay, so if it is electrically isolated, the charge is going to remain same. It's not going to change. So let us start with part A. And part A, we are having isolated plates. Isolated plates, therefore we can say constant charge. Constant charge. And that constant charge is nothing but our Q. So based on this we can find out the energy of the system. So we can see our energy. Energy of the system, that is our U, will be equal to our charge square upon twice capacitance. So we can write this as Q square upon 2 alpha times X. Okay. Now we are going to find out the force, and force we know is nothing but our derivative of our this energy. Okay. So we can say that the force which is F will be equal to a partial derivative of our U with respect to our X for a constant charge Q. Okay. And this negative sign is nothing but it tells us that the force tends to decrease the energy. That's the only purpose of that. And we substitute value of our U. So this we get this as a negative partial derivative, and U is our Q square upon 2 alpha X. And from here we get that the force will be equal to, this will be X square minus plus, so giving us Q square upon 2 alpha X square. And we know that our capacitance is nothing but our alpha times X. Okay. And so from here we can write, if we multiply, so we get this is alpha X square is equal to C times X. Okay. Or this can be written as our C square upon alpha. So therefore we can write that value of force is our Q square upon 2 times alpha upon our C square, or we can write this will be equal to our okay, we can just sort it out, that's not much of a problem. This will be Q square and this comes at 2CX. And if we want to write, we can also say that our force per unit length. Okay, therefore we can say that the force will be equal to our U upon X, and let it be. There is no need to solve this further. Okay, we can keep as it is. And so this will be our value of our force. There is no need to solve further, okay, because that was required. Now we come to our part B, and part B, now the battery has been connected. Part B, we have our connected to battery. So obviously potential will be constant. So you can say constant potential. That is about phi. And in that case, we can write that energy which is over U will be equal to over half C potential square. So we already know C is of alpha times X times potential square. And so it means as battery is connected, so that will be resulting in our constant potential. Okay. And we can easily solve this. That's not much of a problem. Okay. So we can say that the force on the plate will be associated by the change in the total energy of the system, and here the total energy will be now associated with our capacitor as well as our battery. Okay. So we can say that our force will be associated with total energy and this total energy will be consisting of our capacitor as well as our battery. And if we assume that the plate moves by a distance of dx, you can say that our plate moves by dx. Therefore, the energy of the capacitor, say capacitor energy, that is our duc, will be equal to over half potential square and change in the capacitance. And there will be also the battery charge change. So we can say that our battery charge change, and let us put that is our dq. dq will be equal to potential times the change in our this capacitance. Okay. Therefore, from here we can write that the work done by the battery work, that is our dw battery, will be equal to minus of the potential times the charge, and this comes as our phi square times our dc. And now we can easily use our energy conservation. So it means our energy conservation and this energy conservation will be equal to, because the work done, that is a mechanical work done in moving the plates, which is F dx, plus the energy that will be associated with our this capacitor, that is a duc, will be equal to the energy from the battery. So from here we can say that because of our work done because of mechanical force plus energy associated with the capacitor will be equal to the work done because of our battery, because battery is connected to the system. Okay. So it means the entire energy will be equivalent to the work done by the battery. Okay. And we can but in this case we have to remember that the force is moving the plate to the left side, and so x is going to increase. Okay, so we have to remember this. I think we have to change this formula because this was our plate and the overlapping distance is given to us as x, and the plate is moving towards our left side. So obviously this x is going to increase, and if this x is going to increase, so it means that the work plus battery is going to give us a change in stored energy. Yes, so we have to write it otherwise. Therefore we can say that our f dx plus our battery is equal to the capacitance. Now it is correct one because the x is going to increase. Okay. Now we can easily substitute we know that for our energy associated with the capacitor is our half C potential square, and we know that our charge is equal to capacitance multiplied by the potential, and therefore from here we can say that our small charge will be equal to our potential multiplied by the change in small capacitance. Therefore we can write that our f dx plus phi square times change in capacitance is equal to half square times change in capacitance, and we can rewrite this equation as f dx will be equal to minus, we can just solve this will become as minus potential square change in the capacitance. Okay. And we can write this further as minus 1 by 2 potential square is equal to over C upon x times dx. Okay. So from here we can easily see that our negative sign indicates that the force opposes the increasing of the x. Okay, because if we are moving this sliding portion with a force of F, then this x is going to increase. But now under this condition we have connected a battery to this. Okay, we have to remember this part. Okay. And therefore we can say that our and what else is left. Okay, so I can say that my force F is equal to minus 1 by 2 C phi square upon x. So we got the formula for our force. And in part C we have to verify that we got two values of force in part A as well as part B. Okay. So let me write it here. From part A, that is F of A is equal to Q square upon 2cx, and in part B only magnitude sign we are going to just ignore, so this comes as a phi square upon 2x. Okay. So we got these two value of forces, and we have to prove that they are equal with each other. Okay. So we have part C, we have to prove that forces are equal. We have to prove Fa that we got in the option A answer will be equal to force which we got in the option B. And we have to remember in part A, because the capacitor were isolated, so charge were constant. So we can say in part A our charge was constant because the capacitor were isolated. Therefore we can say that the voltage at any instant will be equal to Q upon C. And in part B, battery has been connected. In part B, battery has been connected, therefore the potential is constant. And therefore we can say that at any instant the charge will be equal to capacitance multiplied by the potential. And so in our option A, we got that our f of A is equal to our Q square upon 2Cx. And in this case, this Q is our fixed in part A. And for part B, our potential will be equal to our charge upon capacitance. Therefore, we can write that value of force is equal to our C upon 2x times Q upon C whole square. And this comes as our Q square upon 2Cx, which is nothing but our f of A. So it means the value of force is our same. Okay, it is not going to change. So f of A is equal to f of B. We can do the reverse also. We can put charge is equal to our this. We can put this particular equation also and prove that our f of A is equal to f of B. Okay. So we got the value of forces in part A as well as part B. And we have to remember in part A, it was an isolated system, so the charges were constant. Q was constant. And part B, now the plates of the capacitor were connected to the battery. So in that case, our potential, that is our phi, was constant. So this completes all the 4 questions for today. Thank you.